This video is probability, the multiplication rule part 2. We're picking up with the multiplication rule for dependent events. So let's look at this scenario. About 15% of adult men in the United States are over 6 feet tall. That means if a man was chosen at random from the population, the probability that he would be over 6 feet would be 0.15. Now, if I give you some extra information and I tell you that the person selected is a professional basketball player, do you think that the probability is still 15%? Well, professional basketball players are pretty tall, and I would say a good majority of them are over 6 feet. So, knowing that the person chosen at random is a professional basketball player, I would think the probability that they would be over 6 feet goes up. It definitely increases. All right, so conditional probability. On the previous screen, I gave you the condition that the person chosen was going to be a professional basketball player, and that changed things. So that was a condition that happened. So a conditional probability is the probability that event A happens on the condition that event B has already happened. The notation that we use is P parentheses, and then you list the first event, a vertical line, and then the event that already happened. So the event that we're trying to find the probability of, given that the event B has already happened. And see, we would read it as find the probability of A given B, meaning find the probability of A given that B has already happened. And the formula is finding the probability by finding the number of occurrences of A and B together, and then dividing that not by the total of everything, but the total of B, of the given. So if you think back to part 1 of the video, we talked about drawing 2 aces, and we said what's the probability that both will be aces. And we understood that when we drew the first card, it was not going to be replaced. So using the multiplication rule, we did the probability that the first was going to be an ace was 4 out of 52. And then the probability that the second was going to be an ace was different, because if we don't return the first card, that changes how many cards are in the deck. There's now only 51 cards in the deck, and only 3 of those are aces, not 4. So if you look here at the example and you look, this is how we would write the notation out to set it up. You would still multiply down here to get your answer, but I just want to show you that what you're doing is you're finding the probability that the first card is an A or an ace, and then multiply that times the probability that the second card is an ace, given that the first card was an ace. So given that the first one was an ace already occurred, and that's what changes that second probability. So this is very similar to the regular multiplication rule for independent events. You just need to take into consideration, if they're dependent, how the first event occurring affects the second event occurring. So the formula is very similar. If you'll recall, the formula for independent events was just the probability of A and B was just the probability of A times the probability of B. Now it's the probability of A times the probability of B, given that A occurred already. Alright, let's look at example 6, drawing cards without replacement. If you pull 2 cards out of the deck, what's the probability that both are spades? So if you're doing this, you would say, what's the probability that I have a spade and a spade? And since these are dependent because we're not replacing the card, and that's going to affect the probability, it's the probability of a spade times the probability of a spade, given that the first one was a spade. So the probability that the first one is a spade is 12 out of 52. And the probability that the second one is a spade, and I'm sorry, going backwards, 12 out of 52 was wrong. That is wrong. So let me erase that. All right. How many spades are there in a deck? Let me count again. It should be 13 out of 52. Now, assuming that the first card was a spade, given that the first one was a spade, what's the probability that the second one is a spade? Well, now, if one spade has been taken out of the deck, there's now only 12 spades out of 51. And 13 over 52 times 12 over 51 gives us 0.0588. 0.0588. All right, here's another example. You can pause it if you want and see if you can work it out on your own, and then we'll go over the answer when you come back. All right, sock colors. In your drawer you have 10 pairs of socks, 6 of which are white. If you reach in and randomly grab 2 pairs of socks, what's the probability that both are white? So this would be dependent because you don't replace the first pair when you're grabbing the second pair. So one will affect the other. So what's the probability that you have a white and a white? So we want the probability that the first one's a white times the probability that the second one is a white, given that the first one was a white. So let's see. We had 10 pairs of socks, 6 are white, so the probability that the first one's white is 6 out of 10. The probability that the second one is white is not 6 out of 10 because we pulled out a white sock, which leaves 5 white socks out of 9. So if we have 6 over 10 times 5 over 9, that gives us 0.3333 repeating, which we would round to 0.3333, which is the same as 1/3. All right, another example. Why don't you go ahead and pause the video and try this one as well. So we have a bag of M&Ms, and it contains the breakdown of 12 reds, 18 yellows, 24 browns, 22 blue, 13 orange, and 17 green. And if I added these correctly, I think that I did, there's 106 total M&Ms. And I just added these numbers together. All right, so what is the probability of drawing 2 reds? So that's the probability that the first one's red and the second one's red. Now, this was without replacing a candy after each pull. So you're going to find the probability that the first one's red and multiply it times the probability that the second one's red, given that the first one was also red. So red is 12. Let me fix that. Don't know why it does that, but all right, 12 out of 106. And then, assuming that the first one is a red, that leaves 11 red out of 105. So 12 out of 106 times 11 out of 105 gives us 0.0119. 0.0119. So what is the probability of drawing a blue candy and then a red candy? So what is the probability of drawing a blue and then a brown. So we're going to do the probability of a blue times the probability of a brown, given that the first one was blue. Alright, so the first one being blue will be 22 out of 106. And the second one being brown, there's still 24 brown, but now it's only out of 105. So 22 out of 106 times 24 out of 105 gives us 0.0474. Alright, the probability of not drawing two green. So there wasn't enough space, so I've got a screen up here for us. So the probability of not drawing two green is the same as 1 minus the probability of drawing two green. And that would be the same as saying the probability of a green and a green. So the probability that the first one's a green times the probability that the second one's green, given that the first one was green. Now, hopefully I remember correctly, there were 17 greens. So we have 1 minus 17 over 106 times, if we take out a green, that leaves 16 green out of 105. And then if all I did was find the probability of this part right here, 17 over 106 times 16 over 105, that would give me the probability of drawing two greens. To find the complement of it being not two greens, I would subtract that from 1. So you can just type this whole thing in your calculator. You can just type in 1 minus 17 over 106 times 16 over 105. And it looks like you get 0.9756. Alright, and it looks like that was the last slide. So if you have any questions on the multiplication rule or complements, let me know.